Alright, so suppose we have a scale. Okay, it can be a meter scale. Meter scale would be 100 centimeter. Okay, or a 50 centimeter, a half meter scale. If it's a meter scale, in that case, its center of gravity, that means its entire mass would be concentrated at 50 centimeter. That would be right at the middle. Okay. Similarly, if it is on half meter scale, in that case, it will be at 25. Suppose the length is entire length is suppose this length entire length is 50 centimeter. In that case, the center would be at 25. Now, if this scale is pivoted, okay, so it will be called as a fulcrum at the center of mass, that is at 50 centimeters. It will be in equilibrium, that means it will be balanced. All right, but suppose if I put some weight over here on the left hand side, okay, this weight will apply some force, some moment, okay, and it will move in a this direction, okay, that is an anti-clockwise direction. This will generate an anti-clockwise moment of force. Okay, this is a common sense. Okay, if you put a weight, if I put the same weight on the right hand side, in that case it will generate a clockwise moment of force. Okay, so the ruler will start moving in a anti-clockwise or a clockwise direction. If I put an equal amount of weight, say if I put again same amount of weight, in that case it will get balanced. Suppose if this weight is not there over here, if I put only this weight, in that case it will move in this direction, that is in a clockwise direction. So scale will move in a clockwise direction. That means if I by putting a weight, what I'm doing is I'm applying a force, okay, which will move the scale either in a clockwise direction or anti-clockwise direction, depending upon how much forces I'm applying on each arm. All right. Similarly, suppose this scale is balanced, there is no weight on it. Okay, it is balanced at this point, that is at 50 centimeters. Okay. Now, what will happen if I move the fulcrum or the point where the scale is pivoted, okay, on the left hand side? Now, in this case, what will happen is, it's a common sense, the scale will go in this direction, that is in a clockwise direction. It will rotate in a clockwise direction. Similarly, if I move the fulcrum on the left hand side, on the right hand side, in that case it will move in an anti-clockwise direction. Okay. So we understand that by changing the amount of force and by changing the distance, we can make the scale rotate either in a clockwise direction or in an anti-clockwise direction. Now this will give us a principle of moment. Okay, so this is a very important principle because half the numericals in this chapter are based on this principle. It's a very simple one. What it states is, so according to the principle of moment, whatever the force that you are applying, suppose this is a force or this is the weight you have put in, say W1 is the weight and this is W2 is a weight over here. Now this weight W1 and W2 would be equal, okay, if the distance, this distance is equal. So this is, suppose this is L1, okay, length from the fulcrum, and this is L2, length from the fulcrum. So whatever the torque generated by the weight 1, so we know torque is equal to force into distance. So weight 1 would be applying some force which will generate some torque over here, and this is the length for it, L1. Weight 2 will be applying some force which will generate some torque over here, and the length is L2. So torque over here would be W2 into L2, and over here it will be, say this is torque 1 and this is torque 2. So here it will be W1 into L1. So according to the principle of moment in equilibrium, sum of anti-clockwise moment is equal to sum of clockwise moment. That means whatever anti-clockwise moment is there, okay, that means whatever the, because of the force, whatever the moment that has been created, or this moment, anti-clockwise moment on the scale is generated, okay, if this is in equilibrium, this will be equal to it. So So sum of anti-clockwise moment, so whatever the moment is generated because of this length and because of this weight should be equal to this weight and this length. Okay, so remember this, sum of anti-clockwise moment is equal to sum of clockwise moment. It is also represented as W1, so weight 1 into length L1 is equal to W2 into L2. Now one more thing that you should remember, that this is saying, it says that sum of anti-clockwise moment. So suppose if I put one more weight over here, now it will also generate anti-clockwise moment, right? Since it is on the left hand side, it will generate an anti-clockwise moment. Okay, so you have to add them. Okay, whatever this weight is, it should be equal to the sum of clockwise moment. Okay, so according to, so whenever in your numericals, if they say a body is in equilibrium or in an horizontal position or it is balanced, okay, that means W1 into L1 is equal to W2 into L2. That is, if these words are coming, equilibrium, balance or horizontal, that means the weight on the left hand side is equal to weight on the right hand side. Okay, or the sum of anti-clockwise moment is equal to sum of clockwise moment. It's not the weight, it is the sum of anti-clockwise moment is equal to sum of clockwise moment. Okay, so whatever the torque that is generated by this moment would be same as this moment. Okay, a better example for understanding is a beam balance. All right, so a beam balance, whatever weight you put over here, since the length is constant, okay, length is not changing. Okay, the whatever weight you put over here, the same weight it will give over here. So you can calculate if you have this three information, since here length is same, whatever weight this three information you have, you can get this fourth information. All right, okay, that's it. Thank you. Bye.